Okay, so if no questions, so let's start then. So let me share. Okay, so today we are going to discuss about various properties of semiconductor, uh, mostly the concepts that we have developed for metal. So how that we can use to understand semiconductors, we will look at that. So when we talk about semiconductor in terms of the band structure, so the schematic band structure is something like this. So you have a conduction band and you have a valence band, and normally your valence band is full and your conduction band is empty, and you have a band gap, the difference between your conduction band, the bottom of conduction band and the top of the valence band, so that is your band gap. That is how a semiconductor is normally defined when we consider the band structure. Uh, but this is a situation when you are at T equal to 0 Kelvin. But if you increase the temperature, so what happens is there is a lattice vibration that takes place, and due to the lattice vibration, so it is possible that some of the bonds can break, and that will lead to a thermal excitation of electron. So what can happen is, so, so if you have electrons here, so these electrons, they can go to the conduction band due to the thermal excitation. Okay, so this is when T is greater than 0 Kelvin, so there will be thermal excitation, and this is due to the, basically this energy comes from the lattice vibration or the atomic vibration. So these atoms, they vibrate, and it can lead to a breaking of bond, and that will actually lead to a release of electron, or create a free electron which can go to the conduction band. So when you do this process in the thermal generation or thermal excitation process, so if you excite an electron, so you also have creation of holes as well in the valence band. Okay, so the question is about graphene. So the band gap and conductivity is different. So conductivity depends on, so let's say if I have electrons, and if I say I have there's a good conductor, so that means the electron will move without much scattering. Okay, so band gap doesn't play a role in terms of let's say deciding. So it has some significance in terms of conductivity, but it is not, let's say, related to the motion of the electron when you are applying a voltage. So band gap only says that whether there will be electrons in the conduction band or not. So if I talk about semiconductor, but if I have a metal, and now when I talk about conductivity, I will only concentrate on, or let's say, conductivity of the electron. So I will only look at the this band here. So I will focus only on the conduction band and see how the electrons, how fast they can move in the conduction band. I mean, if they can move faster, so then conductivity will be high. Now, if you look at graphene, graphene is a very, it's a two-dimensional material where it is like a carbon-carbon bond is, it's a hexagonal uh, structure. Okay, so it's known as a honeycomb structure, and the carbon-carbon bond is different. Okay, and the energy, the band structure is different. So it is not a, there is no band gap, so to say, uh, in graphene, and that is why so electrons when they are moving, so in graphene they move really fast. Okay, so the mobility is very high because now the electrons in graphene they move only in two dimensions, so not in a three-dimensional like crystal in general. So what we are talking about, all about three-dimensional crystal, but in graphene, so only they move in the plane, in a two-dimensional plane, and they move at a very relatively high velocity. So that is of the order of even very, so they are called as relativistic electrons actually. That means the speed with which these electrons move is very close to the speed of light. And that's why your mobility is high, and that's why conductivity is high. Okay, is it clear, Devans? Okay, uh, so now when you have this conduction band and valence band, so you create electrons and holes. So what we have is generation of electron and hole pairs. So that means when you create an electron, so at the same time you are creating a hole as well. So that's why we call it an electron hole pair. And so when we generate, so this is a statistical process. It is also possible that electron can come back to the valence band and recombine with the hole. Okay, so what generation also means, there is a process recombination can also happen. Okay, that is also possible. So you have, so due to the thermal vibration, the thermal energy that you get from the atomic vibration, so they can generate electron hole pair, and then electron can de-excite and also recombine with the hole. And what would happen in that process when the recombination happens? So this, let's say, jumps to the valence band, so it will in the process, so you will have a generation of a photon, or a light will be emitted with certain frequency, where your frequency or the energy of the photon that is generated, so it is h nu or hf, whatever you want to call. So this uh, energy of the photon that is that you get due to this recombination process will be equal to the band gap, and that is what typically used in a light emitting devices. Okay, so if you take a LED, a light emitting diode, for example, or any device, light emitting device, so in that, so what you have is a process, a recombination process happens where a photon will be generated. Okay, so at a thermal equilibrium, so when your semiconductor is at thermal equilibrium, so you have some equilibrium concentration of electron and hole pair. Okay. So now what happens to the band when you are applying an electric field? So if I am applying a voltage to the material, so what would happen to this band structure, the schematic structure? So let's look at what happens to the, so let's say this is my material, and now I am applying a electric field, Ex, okay? So the potential will vary something like, so if I plot the potential as a function of X, so it will have a negative gradient, okay? Or if I plot the potential energy of the electron in the material, so the potential energy will be, let's say, some minus EV here, so minus EV, and it will be like going, so on the other side it will be high. So let's say something is like a 0. So if I say potential difference is V, that is the voltage I am applying. So how this will change the band structure? We already saw that in case of metals. So what happens is a bending of the band. So if I have a conduction band, let's say now I'm just looking at the conduction band, okay? So I have many such energy levels, tiny energy states or energy levels in the conduction band. Now in presence of electric field, so if I am applying a field like this, so there will be a bending because of the potential energy, this electrostatic potential energy. So I have a bending of the band in this way. So there is a slope here, a linear slope, which is again, all the energy levels will be affected by that. And now if I say I want to move the electron in presence of the field, so here I have applied a field Ex. So what would happen to the electron? So electron will basically will move. So since there is a slope here, so electrons would like to drift towards, I mean, they roll down the hill in a way, and that will give rise to the motion of the electron and eventually a current. So what would happen here inside the band? So it can happen that electron can go from this energy level to this one due to this slope or due to the drift, which we call the drift of the electron. Now, once the electron is here, so it is possible that there is a scattering can happen, and then it will come back to this energy level, and then again it will be accelerated due to the electric field, and then keep on going from one end to the other end, and you get a electric current. So this is a situation with electron. So what would happen with hole? Hole also would look very similar, only the behavior will be opposite to that of electron. So because hole is a positive charge, so when we say the potential energy of electron is lower on left hand side compared to the right hand side, and therefore this is the slope that we get. So again, the band would look very similar, the bending, only the motion of the hole will be different. So let me do that. So in terms of the electrons, what we are plotting is electrons energy levels. So they will exactly will have the same slope like the conduction band. However, the holes, they will have a different movement. So the hole has a lower energy on this side or a higher energy on this side, because it is exactly behaves opposite to that of electron. And when we say the movement of hole in the band, so we say it will go something like this, let's say somewhere here, and then it will scatter. So if there is a scattering process, so it will go back to this level, okay, and then again it will get accelerated. So this is the situation with electron. So what would happen with hole? Hole also would look very similar, only the motion of the hole will be different. So let me do that. So in terms of the electrons, what we are plotting is electrons energy levels. So they will exactly will have the same slope like the conduction band. However, the hole, they will have a different movement. So the and then scattering and so on. And that is how the hole will move from one point to another point in the crystal. So remember, hole is nothing but a unavailable electron state. So when we say that a hole moves, that means what exactly is happening is actually electron moves and occupies that vacant state, and we say basically the this empty state actually drifts. So that is how. So it is not like some empty state that is actually drifting in reality. In reality, what is happening is again electron is drifting, okay, in the valence band as well. But we say it in a way that this empty state, so it is equivalent to an empty state or this hole basically drifting in the valence band. Okay. So what would be the conductivity of the material then? So the conductivity is, we will write the conductivity again using the classical form. So will be equal to E 10 into V drift plus E, E and V drift of hole. So what is, so the charge, electron and hole will have the same charge. What is N? N is concentration of electron, and P is concentration of holes. So the drift, this is a drift velocity of electron, and VTH is drift velocity of hole. So this drift velocity will be related to your mobility, something like this. This is mu h. Okay. So this is the conductivity of the semiconductor, and mu e is the mobility of electron, and mu h is mobility of the hole. And what is mu e in terms of? So let's say write down. So which will be equal to E tau by m e star. Mu h will be mobility of hole, which is again E tau by m h star. So now we are saying that hole also has a mass. It is not like any, it behaves almost like an electron. So it has charge, it also has a mass, and therefore it has mobility. And that is how you will get a resistance due to the movement of this hole. Okay, so this effective mass basically says that there is a resistance to the motion when a hole is in an electric field. And this conductivity that we say we wrote is in terms of the classical Drude model. So here we are saying both electron and hole will contribute to the conductivity, which is always true for a semiconductor. Okay, so here we are assuming that one thing which remember we are assuming here is it's like a classical free electron model. So we are not using a quantum mechanical formulation where we saw a different result in case of metal. Now, if we want to calculate the conductivity, so we want to know what is, So two important quantities that is really useful in semiconductor. They are N and P. So the concentration of electron and P. So if we know this N and P, so we can then calculate what is the conductivity. Then how do we calculate this N and P? So then we again take a concept that we already developed about density of states and the probability distribution. So we can say that our N E in a conduction band, let's say, would be equal to G conduction band and the electron probability distribution, the Fermi-Dirac distribution. So G is your density of state in conduction band. So this is density of state in conduction band, and this is your Fermi-Dirac distribution, or the probability distribution of the electron. And if you want to calculate the total number of electrons in the conduction band, so we will then integrate it over the whole band, EC to E top, okay, and NE into DE. So if we do the integration, so we will get the total number of electrons in the conduction band. So let's look at a picture, a graphical picture of that, and try to understand this, what will be the value of N. So I am just plotting the conduction band here. So the valence band would be somewhere here. So I have electrons in the conduction band, okay, and what will be, so this is my energy axis. So what will be the GCB? So it is a e to the power half dependence. So it will be like something like this, okay. So this is your, how the density of states would vary as a function of energy. Now how your probability distribution would vary as a function of, oh sorry, in this axis always I have E, and I'll plot f of E. So this will vary something like, if you remember, so we have some states will be occupied above the Fermi level, and most of the states, so this is f of E would be, this is 1, this is 0.5, okay, and so some will be, some of the electrons are the probability of occupying states above in the conduction band. So this is how this f of E would look like. Or maybe this is not 0.5, may not be, so it can be actually a different value because the Fermi level will be somewhere else. But somehow it will resemble to this kind of picture. And now if I plot these two together, so how would look like? So the product will give me the total number of electrons in the conduction band. So it is something like this. Or maybe I can plot it here. So let's plot it in different color. So this is my N E. Okay, NEE. So now if I take the area under this curve, so that will be my N. okay, which is LE integration over the from EC to. So that means this area under this curve will say how many electrons I have in the conduction band. So we can also do some mathematics to understand that, and the valence band is somewhere always here. Okay, so we have the valence band picture. We will draw that later on. So this is how we can calculate N, and one thing which is assumed in semiconductor when we want to calculate the number of electrons. So now mathematically what we need to know, this density of state G and F of E. So F of E is equal to, like if we look at the Fermi-Dirac distribution, E minus EF by KBT. But what we assume is that our C minus EF is much greater than KBT. So what it means, this is one assumption, and which is actually a valid assumption when we look at the physics of it, because I mean, if you even do some calculation, you will see that. So what it means is the number of states, available energy states in the conduction band is much larger compared to number of electrons. So this means the number of available states in conduction band is much larger than number of electrons in conduction band. So that what it leads to is basically the electrons will follow not a Fermi-Dirac distribution, but it will follow a classical Maxwell-Boltzmann distribution, and in that case your F of E will be minus EF by KVT. So it will be proportional to this probability Boltzmann, like Maxwell-Boltzmann distribution. And another thing what you also would notice, that this probability of occupying this F of E will go to really 0 when E goes to infinite. Okay, so now what is G? The density of states. Density of states, we will use the same expression that we had earlier. So M E star by H, H to the power 3 by 2, E minus EC to the power half. So this is the expression for density of states. Now if you substitute that and solve that integral, so we will get an expression for N, which is your, so N is equal to your integration from EC, and we say we can take now, instead of taking E top, so we can take it to infinite, and then we say EC up to infinite, G, C, B, E, and F of E, D, E. Now if you substitute that and do the integration, so you will get a result. So I'm writing down the result now, E minus EC minus EF by KBT. And what is NC is 2 into 2 pi W star KBT divided by H square to the power 3 by 2. So this is the concentration of, so this is the concentration of electron in the conduction band, this expression, where you see it is an exponential dependence on the difference between your EC minus EF, and also depends on NC, which also has a dependence on the effective mass and dependence on temperature as well. Now, if you look carefully or compare this to our metallic case, so here NC will be your kind of a, it describes a effective density of states. So NC is effective density of states, and your this exponential function here, something here, f of e. Okay, so this describes your probability distribution, and NC is nothing but a effective density of states in conduction band. Okay, so we can also do a similar calculation for holes in the valence band. So I will exactly same we can do, and now let's first do the graphical how it would look like. So if I take the valence band now, so I have the conduction band here. Okay, now I have the valence band here, so I have holes in the valence band. So this is my valence band, and now I will plot the density of states. This is my energy axis again. Our energy is increasing actually in this way. And this will be again e to the power half dependence. Okay, and now the dependence is EV minus e to the power half. So what is f of e here? So this is a little bit different. The f of e is different here. So in case of holes, we don't say the distribution is f of e, rather we say the distribution is 1 minus f of e, because the hole, they represent empty electron state. So if I say, so the probability of occupation will be always maximum probability is 1. So now if I know what is the probability distribution of electron, and I subtract, so take 1 minus f of e, so I will know what is the distribution, probability distribution for holes. Okay, so this is, so instead of plotting f of e, so we plot 1 minus f of e, which is basically, we can say the probability distribution for holes. And in that case, it would look like, so the whole probability distribution will be almost 1 when we are in the conduction band, because f of e will be 0. So in that case, 1 minus f of e will be maximum. And then when you come to the conduction band, valence band, so it will be like this. Okay, so very similar to your electron distribution, but the opposite. Okay, opposite of that. And then if I plot the n or p now, so not n, but I plot p of e, because I want to calculate the number of holes. So it will be like this. And now if I take the area under this curve, so that will be my p. So which will be p, 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 p. And this integration will be from EV to 0, the bottom of the valence band actually. So if you do this, the same mathematics we did earlier, so you can do that. So you substitute the value of density of states. Now in, so what is P? E. E is equal to G VVE and 1 minus f of E. So it is not f of E like earlier, so it will be 1 minus f of E. So again, we assume that the same EF minus EV will be much greater than KBT. So we will use the Maxwell-Boltzmann distribution, and you do the same mathematics, and what we will get is expression for P, which is equal to n of V exponential minus EF. Very similar to the number of electrons that we calculated, and what is n of V? N of V is equal to 2 pi m h star kBt by h square to the power 3 by 2. So very similar expression to the one we got for electrons. Okay. So basically, one interesting thing we will observe here. So if I take the multiply the number of electrons and number of holes. So if I multiply n and p, so we have the value of n here is this much, the value of p is this much. Okay, so if you multiply both, so very simple, straightforward answer, what you will get is exponential minus EC minus EF by KBT, and what, oh, EC minus EV, sorry. So this is EC minus EV. Okay, so, and what is that? NC NV exponential minus EG by KBT. So the product of number of electrons and number of holes at thermal equilibrium depends on the effective density of states in conduction band, effective density of states in valence band, and is proportional to exponentially depends on the band gap. So there is no Fermi label involved here, like in metal. So in metal, the value of n depends where the Fermi label is. But in case of semiconductor, this number of electrons and holes, the product doesn't depend on the Fermi label. And this EZ is your band gap, right? So this is your band gap of the material. And this is like a constant, okay? So for a material, so this product NP is constant for a material at a given temperature. And this is always true, okay? So this product at thermal equilibrium, the product of N and P will be constant at a given temperature. So, and this is always true for a semiconductor material. And it does not depend on Fermi label. So what is, where the Fermi label, it is not, we don't care about that. Now, if I say intrinsic semiconductor, so in case of intrinsic semiconductor, N is equal to P, so which we write, let's say Ni, the intrinsic concentration. So the product Np will be equal to Ni square, which is again the same Nc Nv exponential minus Eg by kBt. So this equation is known as a mass action law. Okay. So that means, let's say if you increase the concentration of N, so the product must remain constant. So if you increase the number of electrons in the conduction band, so eventually the number of holes will also decrease at the same time to keep this value constant. And what will be Ni? Ni will be Nc into Nv to the power half exponential minus Eg by 2 kBt. This is your Ni, the intrinsic concentration. And what is the physical meaning of this equation? So the physical meaning is that you have, so the left hand side is represents, left hand side says this is NP, the product is, this NP is a rate of recombination, because the rate of recombination will depend, this rate will depend on concentration of N and P. Because if you increase the number of electrons and number of holes somehow, so the rate of recombination will also increase. And the right hand side represents the rate of generation. So at equilibrium, the left hand side should be equal to right hand side. That means the rate of generation should be equal to rate of recombination. So that is what this equation says. So if you do this a small, again a little bit of mathematics here. So if you, we have two expressions for P. So one is for that we got from this mass action law equation, which is minus Eg by 2 kBt. Another which we calculated earlier using the distribution, which is minus Ef minus Ev by kBt. So now if you equate these two, so you will get an expression for the Fermi level, Ev plus half Ez minus 3 by 4 kBt m star by mh star. And what this means is, so if me star is equal to mh star, so in that case Ef will be Ev plus half Ez. So what it means is the Fermi level will be in between the band gap, exactly half of the, so above the valence band and exactly at half of the band gap, so you will have the Fermi level. So this is this picture that is shown here. So you have the valence band, you have the conduction band, so you have electrons and holes, and the Fermi level is exactly at the middle. So this is your Fermi level. So now you can create N-type and P-type by doping. If you dope a, so you can create N-type or P-type by doping pentavalent or trivalent atoms such as arsenic or boron. Okay. And one thing here you remember when we say about this Fermi level is in the middle, so the work function is still defined. The definition has not changed. So the work function we are defining by the work function phi. Here we have defined like E vacuum minus EF. So that definition has not changed. Although the Fermi level doesn't have any electrons. So because Fermi level is lying in a within the band gap, and that means this is a forbidden region for the electrons, and electron cannot occupy any state within this energy. So that's why a Fermi level, there will be no electrons at Fermi level. In metal, we have like electrons up to the Fermi level, but in semiconductors, there will be no electrons at the Fermi level. However, the work function is defined still the difference between the vacuum level and the Fermi level. And what this Fermi level will change depending on the doping. So if I put a more dopants or N-type, if I have an N-type situation, so the Fermi level will move close to the conduction band. And if I have P-type, so where I dope a boron, for example, so the Fermi level will move close to the valence band. Okay, so this is again, there will be difference in the Fermi level, the height of the Fermi level or the position of the Fermi level within the band gap. And it is always within the band gap. It is not changing or going into the conduction band and valence band. So it is a forbidden region for electrons. And so one significance of Fermi level we discussed that earlier. So the same thing also holds true here. So that delta EF will be equal to 0 in the material. Unless if you are, when it will be non-zero? Only when you are applying a voltage or like illuminating it. So if you are not doing anything externally, so this delta EF, or the Fermi level will be always the same throughout the material. So if there is a slope in the Fermi level, delta EF, then in that case it will lead to a drift of electron, and which can only happen when you are applying a voltage, or maybe you are shining a light or giving some external energy or thermal, or heating it, or thermal energy, like that. Otherwise delta EF will be always 0 in a material. So this is similar to like you have a potential energy. I mean the material would that the potential energy would be the same everywhere unless you are applying an electric field. And the average energies will be in a conduction band, let's say, will be 3/2 kBt. In case of, this is in case of semiconductor, because it again follows from the Maxwell-Boltzmann distribution, but in case of metal, it was 3.5 into EF in case of metal. So which is not a temperature dependent term. Okay, so very different average energy of electron when they are in metal and when they are in conduction band of semiconductor or valence band of semiconductor. So that means the electrons in the conduction band, so they don't follow the Pauli's exclusion principle. Okay, so here they don't follow Pauli's exclusion principle. They don't follow. And the reason again is because you have more number of states in the conduction band compared to available number of electrons. So the number of electrons are much less compared to the number of states, and that's why you have less number of, or they don't follow the Pauli's exclusion principle, or you can say it is neglected. Now if I say, so this is all about the intrinsic semiconductor. So when we say about extrinsic semiconductor, I think maybe I have, yeah, it's almost time. So we will stop now, and we'll continue then in the next class with the topic on extrinsic semiconductor. So, yeah, any question? Okay, so if not the case, then we stop for today, and we will meet again on Wednesday. Thank you.